Okay, so we can start. Good afternoon and welcome. Today's speaker is Pietro Benetti Genolini from Cambridge, and he will tell us about instantons, symmetries, and anomalies in 5 dimensions. Let me remind you once again that you're encouraged to ask questions. Just ask me the microphone, and people online can just open up their microphone and ask their questions.
Thanks. I would like to start by thanking the organizers for inviting me to give the talk and for inviting me to GGI. It's been great. It was my first time at GGI, and I'll be back soon, hopefully. And it's great to be back to an in-person conference. I think I share this impression with everyone here. And in the spirit of being old-fashioned, I will also give a Blackboard talk. And this is work that I've been doing with Luigi Tizzano, who's here in the audience, since 2020. This is the archive number, not the year. And I'll start. Okay, so actually, before we begin the actual talk, I need to say a few words about higher form symmetries in advance of the talk, of the informal talk that will happen on Friday. So I hope I don't spoil anything for you, but just to set notation and put everyone at the same level. So an ordinary continuous symmetry is associated to a current that is conserved. And we say that the charge of the charge that is enclosed in a d-1 dimensional space volume is given by the integral over sigma d-1 of star j. Right, so this is the standard presentation, and because thanks to Stokes' theorem, the dependence of Q on sigma d-1 is actually topological in the sense that if you deform it, it doesn't change Q because of Stokes' theorem. However, there is perhaps a more generalizable picture of this. So rather than focusing on the current, we should rather focus on the operator sigma d-1. So we say that to an ordinary symmetry, we associate an operator U that depends on a group element and to sigma, and we say that we require that the dependence on the topological on the space is topological in the same sense. So if you deform it, it doesn't change. And G is the group element that is associated, and it will satisfy some group law. So if you put them at the same point, you will find this. And for the relationship with this is that this is just given by provided G is equal to e to the I alpha. So first, you notice that this can be generalized in at least 2 directions. So first, I haven't talked about the current, so I can talk about also discrete symmetries, so long as I say how it acts on local operators. So if I insert a local operator O at X, then I say that the action of this operator on the local operator, the action of the charge operator on the charged operator so if O transforms in some representation G, some representation R of the group, then it's like this. When I deform sigma d-1 to a sphere that surrounds the point, and I shrink the sphere to 0. Okay, so this is a first generalization. So I never talked about current, so I can talk about discrete symmetries in the same, using the same formalism, but I can also generalize this using in a different direction, because I can change the dimension of this operator. So in particular, I can introduce codimension 2 operators, and I say that codimension 2 operators, again, U, G, sigma d minus 2, implement one-form symmetries. Okay, so immediately I see that because I don't have an ordering of codimension 2 operators, of codimension 2 spaces, there is no way of ordering them in space-time. One-form symmetries must be abelian, so I can move them around, and they act on lines rather than on local operators, because codimension 2 surface can only link a line. So in this case, the action on the line supported on gamma will be given by, again, same as I shrink, as I take sigma d minus 2 to link gamma, and I shrink it to 0 around gamma. Okay, so the picture to have in mind is this. As I take in 3-dimensional line links a line. So I take the line, this is the line W gamma, this is the line implementing, sorry, sigma 1. And then as I shrink UG, I only get a factor and the same line, W gamma. Okay, so this is a one-form symmetry, and they have to be abelian, but they can also be discrete. The important point is that they act on lines. This is what you should remember. Okay, so let's begin. Now that we have introduced this new concept of symmetries, we should also try to understand whether they improve our knowledge of field theories, or whether they improve our knowledge of physics. In particular, we can wonder whether knowledge of these symmetries leads to knowledge about their anomalies. So they can be anomalous, and we know that anomalies are RG invariant, so they can lead to constraints on the non-perturbative phase of these field theories. But also we should reapply these symmetries, we should review dualities that are already known in light of these symmetries, trying to check whether we can refine them or improve our understanding of these. And this is what we're going to try to do today. Okay, so before going to 5D, I'm going to do an easier example that probably you're all familiar with, you're more familiar with than I am, and that especially after Riccardo's talk yesterday. So we're going to talk about 3 dimensions. So take 2 complex scalars in 3 dimensions. Their symmetry is U2, which can be written as SU2 times U1, modded by Z2. And now suppose that I gauge this U1. Okay, so because it's inside U2, I give both scalars charge +1. So now I have a theory of 2 complex scalars of charge 1 but now it's clear, because of how I have written this U2, that this Zrednicki or Peskin or Nair, whatever example, was actually wrong when we learned about it. The symmetry of the system is not SU2. The flavor symmetry of the system is not SU2, really. It's SU2 modded by Z2, because I can introduce some gauge field which cancels the SU2 mod Z2 part of this bundle. Okay? So let me be more concrete. So SU2 mod Z2, which is the flavor symmetry, is SO3. And the statement that follows from this quotient is that gauge invariant operators always transform in SO3 under SO3 representations and not SU2, which is another way of saying that the faithful group is SO3 or whatever you want to call it in this way. So a bundle, despite the fact that SO3 is smaller than SU2 in really a topological sense, it's half the sphere, it has more bundles. So bundles of SO3 are identified by the Stiefel-Whitney class. Well, yeah, whatever. Which is a characteristic class valued in Z2, which means that its integrals are always in Z2. And a bundle, if you give me a SO3 bundle with non-trivial Stiefel-Whitney class, I will not be able to lift it to a SU2 bundle, which is spin 3. So you may have heard about this in spin context, but it's always the same. And whereas the only bundles that can be lifted to SU2 bundles are such that the Stiefel-Whitney class is W0, is 0. Okay? Now, because of the quotient, the Stiefel-Whitney class and the characteristic class, this U1 gauge modded by Z2 bundle, are related to each other. So if I talk about the gauge, if I introduce a gauge field A, then I find that the quotient implies that the fractional part of what would be the first Chern class of this bundle, f divided by 2 pi, is actually measured by 1/2 of W2. Okay? If something that I say is not clear, please do interrupt me. It works like in online seminars, of course. So this controls the fractional part of the two. And this, I cannot write here C1 because it's not really a U1 bundle. It could be a U1 mod Z2 bundle. Okay, so since I have introduced, okay, so I have a flavor symmetry SO3. What are the other symmetries of the theory? Because I've introduced a gauge field in 3 dimensions, I also have a topological symmetry, U1T, for which the current, so this is a continuous ordinary symmetry, so it's associated to a current, again. And the current is f divided by 2 pi, JT. Okay, so the objects that are charged under this current, this is a very famous symmetry. The objects that are charged under this current are monopole operators, so they are local operators in 3 dimensions that are concretely disorder operators, which means that they are specified by boundary conditions for the gauge field at the insertion point X. And you can check, you can check whether they exist by surrounding the insertion point and measure the monopole charge on the sphere surrounding this point. If it's non-zero, then I have a monopole and so on. So these are our symmetries. However,
sorry.
Yes.
Are you saying that the monopole charge is not integer?
Exactly. So this is what I'm gonna end up saying. So because of the quotient, okay. Can I do it in steps? Cool. So couple U1 to a background gauge field AT. This is a fixed configuration. So this means that I introduce in the Lagrangian a term, sorry, which is charge AT. And now you can see, as Andrea pointed out immediately, that when I do when I perform a large gauge transformation of AT, then my partition function picks up star JT, which is f divided by 2 pi. but f divided by 2 pi is measured by the Stiefel-Whitney class. And this is measuring only the fractional part, right? Because the integer part is irrelevant. Okay, so what have we found? We have found that basically we cannot gauge the U1 topological charge because I can only gauge a symmetry if, when I perform a gauge transformation, the partition function remains identical to itself. Instead, if the partition function varies by a phase, and this phase cannot be cancelled by a local counter term, I cannot gauge this symmetry. This will not be an invariant statement, a well-defined statement. And this is the signal of an 't-Hooft anomaly. In the sense, literally, of an anomaly in the sense of a 't-Hooft. So, which one works better? This one? Yes. Okay. So, let me say a few things that are very important. So, stress things that are probably obvious to all of you, but it's important that they are very clear. So, they don't invalidate the symmetry. So it's not like a gauge anomaly. The theory is still well consistent. It's all fine. However, their importance arises from the fact that they are preserved under RG flow. And this was used by the original 't-Hooft paper to show that confinement implies scalar symmetry breaking. Another important result is that 't-Hooft anomalies can be encoded in anomaly inflow.
Sorry, Pietro.
Yes.
Sorry, a question on the previous blackboard. So these 't-Hooft anomalies are mixed anomaly, right?
So in this case,
and I mean, it arises if you have a background for SO3, right?
Yes. So in this case, it's a mixed 't-Hooft anomaly between the U1T and the flavor symmetry, and that means that that if I gauge one, the other one is explicitly broken.
Oh, okay, so it does not prevent you from gauging it, actually.
It doesn't prevent me from gauging this particular one I was making, yes. If I gauge it, then I will break the other one. So they are included in anomaly inflow from a D+1 dimensional anomaly theory, which is sometimes loosely called an SPT phase. I'm not a condensed matter theorist. There are many more experts in the audience. I think it's relatively the same, but probably SPT requires more careful definitions. But so in this particular case, for instance, its inflow there is a 1/2. Okay, so what does it mean that it's encoded in the inflow? It means that the system Z computed on M3 times A4 computed on Y4 such that the boundary of Y4 is M3 is a well-defined number. Whereas Z alone, as you see there, is really a section of a complex line bundle, right? Whereas the variation of this inflow of this anomaly theory cancels Z, cancels the variation of Z under the gauge transformation. Okay, so this is what we have just discovered. And this is what we're going to now use in order to make some predictions about the dynamics of this theory. So actually, I'm not going to talk about the dynamics of this specific theory. I'm going to talk about the dynamics of a theory for which this is just a subsector. So because I know the dynamics a little bit better. So embed this. Into n equals to 4 SQED. Okay, so with two hypers. It's not important, it's not crucial what this theory is. The important point is that it has these symmetries and they have that interaction as well.
Yes. Sorry, because you started very slowly, I am allowed to ask stupid questions, okay? Or simple questions. This Z2, is this W2 exists because it's a property of the manifold M3, okay? So it is not the property of SO3 you started with. It's a property of the space-time manifold.
Yes and no, in the sense that that W2 is not the Stiefel-Whitney class. So there's a SO3 is also the structure group of the tangent bundle of M3. In that case, that SO3 is not the tangent bundle of it's not the structure group of the tangent bundle. It's the structure group of the background gauge bundle for the flavor symmetry.
Mm-hmm.
So it's not always 0 because, you know, 3 manifolds are spin. You see what I mean?
Yeah. So the question is, W2 is different from 0 or not?
It can be different from 0.
Okay. Depends on the manifold. So that zeta also depends on the manifold you choose. Did zeta?
Yes.
Zeta, you just said that is a functional of the gauge bundle, but not on the depend also on the manifold in which it is defined.
Yes. So it will also depend on other properties.
Okay.
Yes.
Thank you.
So when I embed this into SQED, I know what it becomes in the IR because, well, I know, I'm told. In the IR, this theory flows to an SCFT and I'm told, well, I can check, you know, you can check. There are many checks that you can do in order to support this claim that the U1T is enhanced to SU2 topological, okay? So there are other currents that are massive that become massless and mix with the current for the U1T to make the group non-abelian. However, we see that this is not consistent. This pattern of enhancement is not consistent with anomaly matching for this anomaly. Because if DAT, so the characteristic class for this U1T, has to be embedded into an SU2 class, this would have to be a degree 2 class in SU2. But there are no such classes. The cohomology of BSU2 is 0 in that degree. However, it is compatible with an enhancement to SO3T. In that case, it's just a Stiefel-Whitney class, right? So the C1, the W2 of this bundle becomes the C1 of the U1T bundle modulo 2. And in this case, I would say that the anomaly in the IR, the anomaly theory in the IR, is just a cup product of these two characteristic classes, respectively for the topological, for the enhanced topological bundle, and for the flavor bundle. If you know a little bit more about this n equals to 4 SQED, you would be very happy that this appears, because n equals to 4 SQED enjoys another property, which is just called mirror symmetry, which exchanges, it does a lot of things. But in particular, it exchanges the flavor symmetry, with the topological symmetry. And in this case, because it's self-dual of itself. So it's very good that this anomaly, this infrared anomaly, is invariant under this switch.
Yeah, is this U1T a gauge symmetry or a global symmetry?
Say again, sorry?
Is the U1T that is enhanced to SO3?
It's a global symmetry,
It's a global
right? It's this current is just conserved. It's topological. It's conserved because of the Bianchi identity. So, but it's a global symmetry under which the monopoles are charged.
So you have a zero-form global symmetry that you are sort of promoting to a one-form global
No,
symmetry.
no, no. Here there are no one forms. Here I'm only talking about two zero-form symmetries: the SO3 flavor and the U1 monopole symmetry. And the objects that are charged are local operators, monopoles.
Oh, sorry, we're in 3 dimensions. Okay.
Yes,
Yeah, yeah.
sorry. Yes, I'm still in 3 dimensions. Yes, this is 3D. And that's why you have the mirror symmetry and everything. Yes.
I have a very naive question. So I'm confused. I was confused at the beginning, but now I'm even more confused. So you don't have doublets under this these global symmetries? Because I mean, we also discussed it, but if you say SO3, then you shouldn't have doublets, right?
But
If
they
you-
would not be gauge invariant objects. So the faithful one is SO3.
Oh, so you say that gauge invariants are not doublets.
Yes.
Okay.
Simply because I can construct, so the transformation in the center of this acts in the same way on the two scalars, right? So they act e to the I alpha, e to the I alpha, but then I can cancel that transformation with a gauge, with a, you know, with a proper gauge symmetry, with an appropriate gauge symmetry. Okay. Yes.
Sorry, what about the
The
supercharges?
supercharges.
Are not in like 2,2 or something? No. In the inequality.
Of the flavor symmetry? I don't think so.
Eventually, you have an SO3 times SO3. This is not the.
Well, they definitely don't transform under this,
Okay, okay.
right? That's a topological, only the monopoles are charged under this. You could ask about the flavor, but I don't think that they only transform under R and
Okay.
all the other. Yes. Any other questions? Yes.
So just a comment. Also, this is consistent also with a 4D theory that flows to this theory. So there's an Argyris-Douglas theory. I think A1, A3, and the true global symmetry is actually not SU2, as is often written, but indeed SO3. And this is precisely the dimensional reduction of that.
That's amazing. We didn't know about this check. We need to put it in the paper, Luigi. This is also consistent with all the checks that you can do on protected operators. So this is consistent with the fact that if you expand the superconformal index, you only find representations of the adjoint, which is SO3, and also with the with the Hilbert series of the protected operators on the Coulomb branch for this theory. And again, you only find operators that transform in representations that are also representations of SO3. Okay, basically now I'm going to do the same trick in 5D. That's fundamentally the talk. Okay, so I'm going to move here. In order to do this, I need you to make a little bit of a leap of faith. Well, it's a leap of faith that is embedded into 20 plus years of research. But the fact that in 5D, despite the fact that the Gaussian free point doesn't have relevant operators, it only has irrelevant operators. The gauge kinetic term is irrelevant with respect to the free fixed point. There are 5-dimensional superconformal field theories. So fixed points that are strongly coupled and they exist. There are isolated fixed points in the space of theories. the search for non-supersymmetric ones is instead still open. Sorry, inside joke. But okay, so these supersymmetric conformal field theories in 5 dimensions have a flavor symmetry. They are characterized by some global symmetry. And the way you move away from them is by weakly gauging this global symmetry. So you couple a background gauge field for this global symmetry to the current for this global symmetry. And the current belongs to a super multiplet. And the top component, it's the top component. Then you can give a VEV to the other top component of this super multiplet. And this is a relevant deformation in 5 dimensions that makes you flow. And you flow always to a gauge theory. So finally, we are in 5D. In 5D, SCFTs flow to gauge theory by weakly gauging, by giving flavor mass to the global symmetries of the fixed point. So in a supersymmetric context, when you're given a 5D n equals to 1 super Yang-Mills theory, so something that contains this term, you should always think of this as coming. You can think of this as coming from a putative fixed point that has been deformed and flows to here. Okay, not all super Yang-Mills come from a fixed point, but many. In particular, I'm only going to consider one, the easiest one. So there exists an SCFT, which I'm going to call E1, which has with a global symmetry SU2 that I'm going to call SU2I. And it also has the R symmetry, SU2R, and potentially also one-form symmetries. But it definitely has this SU2I. I couple this SU2I, I couple the current of this SU2I to a vector multiplet, and I flow by giving a VEV to the top component. This VEV, which transforms in the adjoint of SU2, breaks SU2 to just a U1I. So I expect to flow to a gauge theory where the gauge coupling is proportional to the VEV that are given to this top component. And the U1I is supposed to be a symmetry of this theory. Okay? Indeed, sorry. And this gauge theory is an SU2 flows. So this is an RG flow to SU2 super Yang-Mills n equals to 1. Okay, so now let's consider, because they are strongly coupled fixed point is really hard to tackle. We're gonna study the gauge theory and then study the anomalies for these symmetries and assume that, well, they are RG invariant, and we're gonna make some assumptions later. But for the time being, I'm only gonna consider gauge theory in 5 dimensions. Okay.
Sorry.
Yes.
Simple question. So is this supposed to be true for any global symmetry in 5 dimensions? So if you have a generic superconformal field in 5 dimensions with some continuous global symmetry,
you can gauge it.
So this it is supposed to always happen that you, I mean, you turn on this top component of the current, you break to the Cartan, and then this gives rise to
yes.
gauge fields.
And this will give rise to that's a SUSY preserving relevant deformation that always flows to a gauge theory with whatever is left of your global flavor symmetry.
Okay.
What it is this E1 theory?
So what it is?
Yeah.
It's an SFT. It's an isolated fixed point in the space of RG flow, or it's an arrangement of D5 and NS5 branes at a certain singularity, or it's M theory on a Calabi-Yau, on a particular singular Calabi-Yau. It's an SDFC that I know exists from other methods, the methods that I just end-waved. And then E1 refers to SU2. SU2 is E1 in the list of affine algebras. And I know that it has this global symmetry. That's everything I know. I'm given, this is the input. You're given this SCFT that is a black box. And now you want to study what are the symmetries of this SCFT. Okay. Can you accept that you're not a very happy?
You have some insight from other methods that it may exist, and then you just analyze the symmetry it has.
Yes.
Okay.
I mean, people write a lot of papers about it. It's a good endeavor, I believe. Okay, so SU2 super young meals though, and then I will try to learn something about U1. So first, there is indeed a U1 symmetry that is called I. That's why I wrote I, because the objects that are charged under this are, so this is a zero form symmetry. And now because I will also have one form symmetries, I will try to remember to write zero form to signify, to mean zero form. It will not happen, but there are only two groups. I know that you can do it. So the objects that are charged under U1I, again, so this comes from the current. Is F with F. So again, you see that the objects that are charged under this is a zero form symmetry. It's a continuous. It's associated to a current. And the objects that are charged under this are again disorder operators. They represent, it's called instantonic symmetry because they represent the uplift in one dimension higher of the instantons in 4D, because you see that the charge is the instantonic charge. It's the instantonic number in 4 dimensions. And they represent disorder operators in the sense that are only specified by boundary conditions for the gauge field at the insertion point. Okay? So this symmetry comes from having broken the SU2I symmetry. That's why that's also called the SU2I. There is also another statement that I will make because I will slip into this lingo, but it's not well defined, which is that this symmetry enhances. This is a non-Wilsonian statement because I'm going up, but really you should always say that SU2I breaks to U1 instantonic, but you know, it's whatever we want. There is also another symmetry, which is the center symmetry. This is typical of all pure Yang-Mills theories. The objects that are charged under this are the Wilson representations in the fundamental, and they transform as, by a phase. So they just rotate by a phase the Wilson lines in the fundamental. This is typical of all Yang-Mills. Now, why is this interesting? So again, let me couple the theory. Let me couple.
Sorry, Pietro.
Yes?
Tell me if I'm spoiling. Is the center symmetry going to enhance the fixed point? Or?
No.
It's known that it's not going to enhance? Or?
It's not known, but the string, so there is nothing from field theory that tells you that it enhances. And the string theory arguments don't see any enhancement of the one form symmetry. So again, couple the U1I to AI. So this means that we introduce in the Lagrangian the same object. And again, as we do large gauge transformation, sorry, plus L deep side, we find that Z where this is the instantonic charge. Okay. However, okay, let me write it in the same way that I wrote it earlier. So this is an integer for a true SU2 configuration because it's just the instantonic number. It's the second Chern class of your gauge bundle. However, when I introduce a background gauge field for the Z2, this is an element B2, is an element B in H2 that I set equal to the SO3, sorry, to the W2. So this is imposed equal to the W2 of the SO3 gauge bundle. So what do I mean by this? What I mean is that when I introduce a background gauge field for the one-form symmetry, it means that I can include in the path integral now also gauge bundles that are really SO3 gauge bundles, provided that their Stiefel-Whitney class is fixed to be equal to B. Okay? It doesn't mean that I've changed the gauge theory. These are observables in the SU2 gauge theory. Okay? However, now I am able to introduce new gauge bundles. And again, SO3 gauge bundles do not have an integer instanton number. In fact, their instanton number I think I write it with a plus so that I'm consistent. So the fractional part of the instanton number of an SO3 gauge bundle is measured by something that is the Pontryagin square of W2, which you can think of as W2 cap W2 mod 4, hence the 1/4. Okay, it's not really this, but it's sufficiently close that you can think about it this way. Okay, so because of this, it means that I have introduced bundles with fractional instanton charge, which means that under a large gauge transformation, I will have a variation of the partition function that is anomalous. And again, I can introduce an anomaly theory, which is written okay, so this is my 6-dimensional anomaly theory that describes the anomalous transformation of the partition function.
Just to be sure, like, could you have phrased also the 3D case in this language of you have some Z2 one form and you turn on a background or not?
Say again, sorry?
Could you have phrased also the 3D discussion in the same language of saying that there is a Z2 one form symmetry and you turn on a background?
The SPT discussion.
The 3D discussion.
No, there is no one form symmetry in 3D. That was the flavor symmetry.
Okay, so there is
no. There was a one form, but that was not what I cared about.
Okay, so it's different.
It's different. The anomaly theory looks very similar, but it's different because in that case, the background field was not a background for the center symmetry.
Okay.
It was a background for the Z2 inside.
Okay.
There is no line that is charged under that symmetry, I think. Maybe I'm wrong. But yes?
So can I mean, I just, do I understand correctly that this background B is something you turn on to make as if the gauge group now is SO3 instead of SU2?
The gauge group is still SU2. I've included, so I set the background, I fixed the background B, that's a fixed source, right? That means that I'm allowed to also include in the partition function as an observable, not as a, also gauge bundles that are SO3. But the gauge theory is still SU2. Yeah, for all intents and purposes, I've not modified the theory because in order to modify it, I would have to dynamic to sum over this in the path integral, whereas here it's a fixed source.
Okay. I'm just saying you have a configuration which looks like an SO3.
Yes, which is an SO3 bundle, but the theory still retains an SU2. The integral over gauge fields that are SU2. Okay. So, okay. So now we are going to consider, now we're going to briefly consider the implications of this anomaly along the RG flow. Okay. The big difference compared to 3D is that in order to conclude anything about the UV, I have to assume that this one-form symmetry is not an accidental symmetry in the gauge phase. Okay, whereas in 3D, I was starting from the UV and I knew where to look. Okay, so I will assume this because otherwise, okay, this is a fairly long talk, but otherwise I wouldn't be able to write the paper. Okay, and also there are string theory arguments in favor of the existence of these one-form symmetries at the SCFT, but let's not go there yet. Okay, so first, no, it's not this. What's this? So first, let's follow this symmetry to the IR. So a 5D gauge theory has a modularized space of vacua. All gauge theories have a modularized space of vacua that are parameterized by the VEV of the... Yes.
Ask a question on it. So, I mean, suppose that it was
an accidental symmetry.
Shouldn't that appear at the fixed point and not all along the RG flow? I mean, if we think of standard RG flow that, I mean, go down, I mean, accidental symmetries appear at the fixed point. No, they are violated by the operators that drive the RG flow. They're not going to exist all along the RG flow. I mean, of course, there are symmetries of the UV fixed point that are broken by the operator that you use, the relevant operator. But
I like this idea because it supports, but I would have to think about it.
Okay.
Sorry. I was going on the Coulomb branch. So there's a moduli space of vacua, the Coulomb branch, which is parameterized by the VEV of the real scalar in the vector supermultiplet. So this is typical of all 5D gauge theories.
So when you have the Coulomb branches, you expect tons of accidental, like higher form symmetries, right? I mean,
the Coulomb branch, yeah, there will be tons.
Yeah.
Yeah. So indeed, now I'm going to show you that there are many. But I can follow. So indeed, so the Coulomb branch for SU2 in this case is just R. There's one real scalar in the vector multiplet, and the low energy theory on a vacuum, the low energy effective theory on a vacuum is just Maxwell. Sorry, it's not Maxwell. It's U1 super Young-Mills with some prepotential that is fixed by the choice of theory. Okay, I'm not going to write it down. But for what is worth, this theory, indeed, as Matti was pointing out, as accidental one-form and two-form symmetries in 5D. However, I am able, you're always able because you're just done adjoint Higgsing. You can always follow the Z2 of the UV inside, inside the U1. It acts simply by shifting the low energy U1 gauge field by a flat Z2 connection. Okay, so in order to follow this, this is the action. And in order to follow this on the Coulomb branch, what you have to do is that you have to substitute, you have to replace F by F minus phi B. So what happens is that your DLL which f, sorry, here there was 8 pi squared, becomes I divided by 4 pi squared, which f. So this is on the Coulomb branch. And this is, if I want to follow the symmetry, this happens because this is the gauge invariant combination of the U1 connection and the background gauge field for the Z21 symmetry. And you see, immediately see if you expand this product, I'm being very loose with notation, this should not be wedge, but if I expand this product, I find a term that is exactly the same as that. I didn't write it down, but it was the anomalous transformation because it's AI wedge B, and I told you that P, the Pontryagin is really the cup, okay? So here I'm being slightly informal. However, I could be formal, so I could introduce a proper Z2 gauge field that is related to A by the fact that their holonomies must be the same. So introduce a Z2 gauge field U, which is related to A by the fact that their anomalies are the same. And you see that the action on A corresponds to an action of U on the Wilson line of U that shows that it's a deconfined line. So U is really the Goldstone mode for the spontaneously broken Z2 one-form symmetry inside the U1. So on U, it acts simply by a shift, which is the typical Goldstone mode, okay? Which is the typical nonlinear action of a Goldstone mode, okay? So now that I have a Z2, now that I've shown that on the Coulomb branch, I also have a Z2 gauge theory, I must be able to couple this Z2 gauge theory to the theory on the Coulomb branch, to the Maxwell theory, in such a way that the anomaly, that the Goldstones take care of the anomaly. This is what you do when you try to write down the Vestumino-Witten term starting from an anomaly, right? You break chiral-symmetry, you construct the Vestumino by making sure that they cancel the anomaly. And what you find is that on the Coulomb branch, you have a TQFT, which is a Z2 gauge theory, together with Maxwell, that takes care of the anomaly, and the gauge field for this gauge theory is the Goldstone mode for the spontaneously broken. For the spontaneously broken Z2 symmetry, okay? This corresponds to the generic expectation that when you spontaneously break a discrete one-form symmetry, you find a TQFT. And here you can prove it. I could write down the action of this TQFT in terms of the Z2. I'm not gonna, but you can do it. Okay, so now you've taken care of the IR, and it works exactly as you expected. So what do you expect in the UV? So first, given what we know in 3D, you immediately can say that, I erased that point too, but you can immediately see that the true enhancement pattern was not to SU2 instanton. It was really to SO3 instanton, right? Because otherwise, I cannot match the anomaly. Again, I have a C1 of a U1I that is supposed to come from breaking a larger group, either SU2 or SO3. But in SU2, there is no degree to characteristic class. It can only be embedded into SO3 with the same in the same way. Okay? Okay, fine. So again, we see that the correct enhancement, the correct statement would have been that I have E1 with SO3 instanton that is broken to U1I instanton, or SO2 if you want to be technically correct. Okay, they are the same theory. Okay, so this is also compatible. This is first. This pattern of enhancement is compatible with everything we know about U1 in terms of protected quantities. So you can compute the superconformal index for this 5D gauge theory on S1 times S4. And because it's protected, you expect that it's the same index at the superconformal fixed point. I think he has a question. Sorry. And you see that if you expand, can I finish the sentence? And if you see that if you expand this index, you only see appearing representations of the adjoint, of adjoint representations of SO3I, which is compatible with SO3. I'm going to give you more compatibility, but first question.
Yeah, I was wondering sort of what the physics of this anomaly means. Is it saying that, I guess what I would have guessed is that it says that the instanton particle is a local operator that's charged under this one form symmetry that only the Wilson line would have originally been charged under. Is that sort of the idea of what this anomaly is telling us?
No, I don't think so. I don't think that's the I mean, a mixed anomaly doesn't necessarily mean that the local operators of one transform under the other.
Oh yes, for
right?
sure.
Yeah.
But it does sometimes.
Yeah.
I mean,
No. The instantons. I don't think that the instantons transform under the center symmetry.
I was just I'm trying to really get a grasp of where this Z2 TQFT, what it really comes from, I guess, physically. Like, I was thinking maybe there's some instanton gas, and since they're charged under this Z2, under the center symmetry, it comes across as a Z2 TQFT.
So no. So here, okay, so thank you for the question. So on the Coulomb branch, U1I is not spontaneously broken. Remember that the objects that are charged under U1I are the instantons, and they are massive. They are ultramassive. Well, they're not ultramassive. They're massive. Their mass is proportional to the gauge coupling. So long as you have a gauge theory description, your instantons will be massive. So they cannot represent an anomaly, right? Massive degrees of freedom can never represent an anomaly because otherwise it would be incompatible with RG invariance. So what you can see though, so then you can wonder, where is this U1I spontaneously broken? So it's not broken it's never broken on the gauge theory phase. It's not broken at the E1 point because we know that it's actually enhanced to SO3. However, at the SCFT point, these instantons become massless. So they become operators, they become BPS operators of your SCFT. And, well, they combine to form the coordinate ring of a Higgs branch of vacua. So until now, I was talking about the Coulomb branch, but there is also a Higgs branch that only opens up at the SCFT, at the E1 point. So the Higgs branch is completely lifted as soon as you go to the gauge, as soon as you do the relevant deformation, because the relevant deformation is proportional to the gauge coupling, which is also proportional to the mass of the instanton, which means that the instantons are lifted. However, at the SCFT, you generically also have protected operators that do transform under SU2R, and when you give webs to those, you parameterize a Higgs branch. In this case, the Higgs branch can be shown to be C2. Well, in 5D, it's an hyperkähler. There's a lot of geometry, and it's very fancy, and it's very cool. In this particular case, it's C2 mod Z2. And again, you find that this is consistent with the faithful symmetry being SO3, because, well, the Z2 represents the quotienting by the representations that are not representations of SO3. And really, when you compute the Hilbert series of chiral operators on this Higgs branch, you find that only representations of SO3 appear. So it's all consistent. This Z2 gauge theory represents a sector of the theory that corresponds to the spontaneously broken one-form symmetry. We want to say that this Z2 gauge theory is not really there only on the Coulomb branch. First, it's also there at the SU2 gauge theory level, because on the SU2 gauge theory level, if you compute the web of a Wilson line, you also find that it's deconfined. That was the problem with finding interesting fixed points in 5D until 1996. But also, it's also there at the E1 point. This is because at the fixed point, you expect deconfinement, not confinement. So you expect the one form to be spontaneously broken. And a spontaneously broken one form corresponds to this Z2 gauge theory. We can derive, so I'm not going to go into the details because they are very technical, but in order to derive the form of the TQFT Z2, you don't need the presence of A. You just need the existence of a Z2 gauge field, which transforms as a Goldstone mode under the Z2 one form, which you believe exists because at the fixed point, it should be deconfined. Your theory should be deconfined. And then, by consistency with the anomaly, again, it's the same procedure that you do for Versumino, you find that it couples to a TQFT, which accompanies your theory along the RG flow. Okay, so these are the, this is basically the conclusion for pure SU2. I will only take 1 minute. So we found an anomaly. We found some of the implications for the dynamics in terms of spontaneously breaking of the one form, and we saw that it matched the anomaly. However, there's also an interesting other anomaly that appears again in the gauge theory with matter. So in the gauge theory with matter, again, you can play, so you add hypers. Hypers transform under a flavor symmetry that rotates them, which, if you consider SU2 with NF hypers, is spin 2NF. However, the center of spin 2NF transforms in the same way as a gauge transformation. So again, like in 3D, you have the faithful global symmetry is not spin 2NF, but is SO 2NF, which is spin divided by Z2. Therefore, you can turn on bundles with a Stiefel-Whitney class, which you set equal to the Stiefel-Whitney class of the SU2 gauge field. You play exactly the same game. You do a large gauge transformation. Again, you have fractionalized the instanton number. Again, you find an anomaly. So in 5D, there is not just the anomaly between one zero form, but there's also an anomaly between the zero form and the zero form instantonic symmetry and the zero form flavor symmetry. Okay, and well, this anomaly also tells you something about these gauge theories and these fixed points. And if you want to know more, you can ask me later. But I think I've exhausted the hour, and thank you very much for your attention.
Regarding your last comment, if this is the case, no, then the enhancement to the full E series, E2, E3, E4, E5, at some point you hit a problem, right? Because E1 is SO2, SO3 is this, you know, but the algebra, but when you go up in E, if I remember correctly, there is an issue because the D and the E series are different, right?
Yes. So
can you comment on that?
So that's a great question. That's still a great problem that we have. So yeah, so as Matteo was saying, so E1 is SU2, E2 is SU2 times U1, and then it goes on, and they're all classical groups until you get to E6, E7, and E8, which are the sporadic groups. So it's weird to find them in terms of characteristic classes. And so we have at least two problems that I don't know the answer to. I think Luigi either, because otherwise he would have written it in the overleaf. First, we don't know how to see from the anomaly the fact that at 7, this stops. So we don't know whether the anomaly tells us something about, spin 14 works, but then spin 16 goes to 6D, but 6D doesn't have, it doesn't work because then, anyway, that's one problem. Also, I am not able to do, which is probably why I can't find the problem at 7. I'm not able to do this trick with spin NF. So again, I have an anomaly that looks exactly like this, where now it's exactly like this, with the difference that this B, rather than being the background gauge field for the Z2 center symmetry, is the Stiefel-Whitney, well, it's the Stiefel-Whitney class of the SO2NF bundle. But the anomaly is the same. And I should be able, I expect that I should be able to find a breaking pattern between, E5 and U1 times spin 10 times SO10 that replicates this. I'm not. But it should be. Was it clear? I don't know. Is that a good? Yeah, so your question is very good, and I don't know the answer to this.
So I have a couple questions, but maybe the first. So for the Higgs branch Hilbert series, I guess everything is probably obvious about the representations. Maybe you just have SO3 representations. But I'm curious for the full index. I mean, I haven't looked at the formulas. I guess these are well known. Maybe the Korean group or something has computed these. Is it easy to prove, like in general, that to all orders you just have, let's say, integer spin representations of SO3, of SU2.
Okay, so I haven't proved it to all orders.
I'm just wondering if there's like an organizing principle that makes it obvious somehow, or if it's just you have to look at some horrible expression and expand it in Mathematica.
So, as far as I see it, you just expand the index. However, you should be able to see, so index knows only about, when you formulate it in terms of gauge theory, the index only knows about U1, right? And you should be able to arrange this the U1 character, the characters under U1I into characters of SO3I representations, and up to order, I don't remember which order, but like 5 or 6 in the sorry. So the 4 in the instantons, 3 in the instantons, I only see adjoint. Full generality. But same for the Hilbert series, instead, there is a closed formula.
Okay, yeah, actually, well, I don't know, maybe I should cut it short, but I don't know, actually I have 2 questions now. So also, I mean, in 4D, there's this protected sector, right? There's this chiral algebra sector. I don't know the story in 5D, but is this another check that you can do? Is there such a sector?
There isn't.
Okay. And maybe finally, so in 4D, again, you have some kind of lens space index, which you can compute, which is sensitive to higher form symmetries. Like, I mean, have people computed some similar partition functions in 5D that are sensitive to this?
They have not. It would be great if they did. So, but in that case, you see the difference between gauge theories, right? So you see the SO3 plus minus compared to the SU2 on the lens space, for instance. Whereas here, you would have to turn on background for the global symmetries as well. So it's even a little bit more complicated.
Okay, yeah, I have a basic question actually. So when you compute the anomalies, no? Okay, what you have shown is like the anomaly in 5D is Z4, I guess, something like this, no?
Is of order 4.
Is of order 4, yes.
Order 4.
But shouldn't it be, is it obvious that the coefficient, I mean, that is the the coefficient in the exponential is 1. Say that it was 4 times that, you wouldn't get an anomaly. So what was the microscopic input to get that? You know?
I was taking a winding I was taking a transformation with arbitrary winding number, and then you find that so suppose you take winding number 1, that's the least coefficient, right? So then you can ask, then you should ask, we did ask, is there a local counter term that cancels this anomaly? And in this case, there isn't. If you had broken this to a Zm, then you would have had some counter terms canceling part of the anomalies and so on.
Okay, I see. No, yeah, because, okay, I just ask you later, no problem.
Okay.
Okay, do we have more questions? So maybe this will be the last one, and then we can continue.
A Pullman question. From this difference between SO2 and SO3 that you highlighted, in the string construction of the 90s, by side there is no indication of such a difference in some sense?
You would see this in like a heterotic, maybe, like not in the PQ web. In the PQ web, there is no difference. Maybe if you did the flow.
I'm speaking about
maybe
the original cyber
the flow. This is not a Pullman's question. This was what
Pullman says that I don't know anything.
No, but this was what Cybergast asked Luigi at the seminar. So
okay, then it's not a Pullman question.
I don't know the answer.
Because in that construction, this I mean, at least naively was like SU2.
But can you see the global form of the group from the singularity?
This is my question, actually. This is the Pullman question. Okay, seriously speaking, this is, I don't know. I'm asking because I'm totally ignorant about
I don't
that.
know. I don't know the answer. Sorry.
Okay, so I think we can close the official part, and then if there are more questions, more discussion, we can of course continue. Let's thank
Thanks.
Pietro again.